In computing, flops is a measure of computer performance, useful in fields of scientific calculations that make heavy use of floating-point calculations. For such cases it is a more accurate measure than the generic instructions per second. Since the final S stands for second, conservative speakers consider flops as both the singular and plural of the term, although the singular flop is frequently encountered. Alternatively, the singular flop is used as an abbreviation for floating-point operation, and a flop count is a count of these operations. In this context, flops is simply the plural rather than a rate, which would then be flops. The expression 1 flops is actually interpreted as computing. One can calculate flops using this equation. Most microprocessors today can do 4 flops per clock cycle. Therefore, a single-core 2.5 GHz processor has a theoretical performance of 10 billion flops equals 10 GFLOPS. Note: in this context, sockets is referring to chip sockets on a motherboard, in other words, how many computer chips are in use, with each chip having one or more cores on it. This equation only applies to one very specific hardware architecture and it ignores limits imposed by memory bandwidth and other constraints. In general, gigaflops are not determined by theoretical calculations such as this one. Instead, they are measured by benchmarks of actual performance throughput. Because this equation ignores all sources of overhead, in the real world, one will never get actual performance that is anywhere near to what this equation predicts. Records, single computer records. In late 1996, Intel's ASCI Red was the world's first computer to achieve 1 TFLOPS and beyond. Sandia director Bill Camp said that ASCI Red had the best reliability of any supercomputer ever built, and US supercomputing unregistered trademark S high watermark in longevity, price, and performance. NEC's SX9 supercomputer was the world's first vector processor to exceed 100 gigaflops per single core. For comparison, a handheld calculator performs relatively few flops. A computer response time below 0.1 a second in a calculation context is usually perceived as instantaneous by a human operator, so a simple calculator needs only about 10 flops to be considered functional. In June 2006, a new computer was announced by Japanese research institute RIKEN, the MDRABE 3. The computer's performance tops out at 1 petaflops, almost 2 times faster than the Blue Gene L, but MDRABE 3 is not a general-purpose computer, which is why it does not appear in the top 500.org list. It has special-purpose pipelines for simulating molecular dynamics. By 2007, Intel Corporation unveiled the experimental multi-core Polaris chip, which achieves 1 TFLOPS at 3.13 GHz. The 80-core chip can raise this result to 2 TFLOPS at 6.26 GHz, although the thermal dissipation at this frequency exceeds 190 watts. On June 26, 2007, IBM announced the second generation of its top supercomputer, dubbed Blue Gene P and designed to continuously operate at speeds exceeding 1 petaflops. When configured to do so, it can reach speeds in excess of 3 petaflops. In June 2007, Top500.org reported the fastest computer in the world to be the IBM Blue Gene L supercomputer, measuring a peak of 596 teraflops. The Cray XT4 hit second place with 101.7 teraflops. On October 25, 2007, NEC Corporation of Japan issued a press release announcing its SX series model SX9, claiming it to be the world's fastest vector supercomputer. The SX9 features the first CPU capable of a peak vector performance of 102.4 gigaflops per single core. On February 4, 2008, the NSF and the University of Texas at Austin opened full-scale research runs on an AMD Sun supercomputer named Ranger, the most powerful supercomputing system in the world for open science research, which operates at sustained speed of 0.5 petaflops. On May 25, 2008, an American supercomputer built by IBM, named Roadrunner, reached a computing milestone of 1 petaflops by processing more than 1.026 quadrillion calculations per second. It headed the June 2008 and November 2008 TOP 500 list of the most powerful supercomputers. The computer is located at Los Alamos National Laboratory in New Mexico, and the computer's name refers to the New Mexico state bird, the greater roadrunner. In June 2008, AMD released ATI Radeon HD 4800 series, which are reported to be the first GPUs to achieve 1 teraflop scale. On August 12, 2008, AMD released the ATI Radeon HD 4870X2 graphics card with 2 Radeon R770 GPUs totaling 2.4 teraflops. In November 2008, an upgrade to the Cray XT Jaguar supercomputer at the Department of Energy unregistered trademark S Oak Ridge National Laboratory raised the system's computing power to a peak 1.64 petaflops, or a quadrillion mathematical calculations per second, making Jaguar the world unregistered trademark S first petaflops system dedicated to open research. In early 2009, the supercomputer was named after a mythical creature, Kraken. Kraken was declared the world's fastest university-managed supercomputer and 6th fastest overall in the 2009 TOP 500 list, which is the global standard for ranking supercomputers. In 2010, Kraken was upgraded and can operate faster and is more powerful. In 2009, the Cray Jaguar performed at 1.75 petaflops, beating the IBM Roadrunner for the number 1 spot on the TOP 500 list. In October 2010, China unveiled the Tianyi, a supercomputer that operates at a peak computing rate of 2.5 petaflops. As of 2010, the fastest 6-core PC processor reaches 109 gigaflops in double precision calculations. GPUs are considerably more powerful. For example, NVIDIA Tesla C2050 GPU computing processors perform around 515 gigaflops in double precision calculations, and the AMD Firestream 9270 peaks at 240 gigaflops. In single precision performance, NVIDIA Tesla C2050 computing processors perform around 1.03 teraflops and the AMD Firestream 9270 cards peak at 1.2 teraflops. Both NVIDIA and AMD's consumer gaming GPUs may reach higher flops. For example, AMD unregistered trademark S Hemlock XT5970 reaches 928 gigaflops in double precision calculations with 2 GPUs on board, and the NVIDIA GTX 480 reaches 672 gigaflops with 1 GPU on board. On December 2, 2010, the U.S. Air Force unveiled a defense supercomputer made up of 1,760 PlayStation 3 consoles that can run 500 trillion floating-point operations per second. In November 2011, it was announced that Japan had achieved 10.51 petaflops with its K computer. It is still under development and software performance tuning is currently underway. It has 88,128 SPARC64 processors in 864 racks, with theoretical performance of 11.28 petaflops. It is named after the Japanese word kai, which stands for 10 quadrillion, corresponding to the target speed of 10 petaflops. On November 15, 2011, Intel demonstrated a single x86-based processor, codenamed Knight's Corner, sustaining more than a teraflop on a wide range of DGEMM operations. Intel emphasized during the demonstration that this was a sustained teraflop, and that it was the first general-purpose processor to ever cross a teraflop. On June 18, 2012, IBM Sequoia's supercomputer system, based at the U.S. Lawrence Livermore National Laboratory, reached 16 petaflops, setting the world record and claiming first place in the latest TOP 500 list. On November 12, 2012, the TOP 500 list certified Titan as the world's fastest supercomputer per the LINPACK benchmark, at 17.59 petaflops. It was developed by Cray Incorporated at the Oak Ridge National Laboratory and combines AMD Opteron processors with a OE Kepler NVIDIA Tesla graphic processing unit technologies. On June 10, 2013, China's Tianyi-2 was ranked the world's fastest with a record of 33.86 petaflops. On April 8, 2014, AMD launched a 9295X2, a dual A9290X in a single PCB, with 11.6 TFLOPS. Distributed computing records. Distributed computing uses the Internet to link personal computers to achieve more flops. Folding at home is sustaining over 20.7 native petaflops as of June 2014 or 43.1 x 86 petaflops. It is the first computing project of any kind to cross the 1, 2, 3, 4, and 5 native petaflops milestone. This level of performance is primarily enabled by the cumulative effort of a vast array of powerful GPU and CPU units. As of July 2014, the entire BOINC network averages about 5.6 petaflops. As of July 2014, SETI at home, employing the BOINC software platform, averages 681 teraflops. As of July 2014, Einstein at home, a project using the BOINC network, is crunching at 492 teraflops. As of July 2014, Milky Way at home, using the BOINC infrastructure, computes at 471 teraflops. As of July 2014, GIMPS is searching for Mersenne primes and sustaining 173 teraflops. Future developments. In 2008, James Bamford's book The Shadow Factory reported that NSA told the Pentagon it would need an exaflop computer by 2018. Given the current speed of progress, supercomputers are projected to reach 1 exaflops in 2019. Cray, Incorporated announced in December 2009 a plan to build a 1 EFLOP supercomputer before 2020. Eric P. de Benedictis of Sandia National Laboratories theorizes that a zetaflops computer is required to accomplish full weather modeling of 2-week time span. Such systems might be built around 2030. In India, ISRO and Indian Institute of Science have stated that they have planned to make a 132.8 EFLOP supercomputer by 2017, 100 times faster than any supercomputer ever planned. They have estimated that the project would cost $2 billion, which the state has budgeted. Cost of computing, hardware costs. The following is a list of examples of computers that demonstrates how drastically performance has increased and price has decreased. The cost per GFLOPS is the cost for a set of hardware that would theoretically operate at 1 billion floating-point operations per second. During the era when no single computing platform was able to achieve 1 GFLOPS, this table lists the total cost for multiple instances of a fast computing platform which speed sums to 1 GFLOPS. Otherwise, the least expensive computing platform able to achieve 1 GFLOPS is listed. The trend toward placing ever more transistors inexpensively on an integrated circuit follows Moore's law. This trend explains the rising speed and falling cost of computer processing. Operation costs. In energy cost, according to the Green 500 list, as of June 2011 the most efficient TOP 500 supercomputer runs at 2097.19 flops per watt. This translates to an energy requirement of 0.477 watts per GFLOPS, however this energy requirement will be much greater for less efficient supercomputers. Hardware costs for low-cost supercomputers may be less significant than energy costs when running continuously for several years. Floating-point operation and integer operation, FLOPS measures the computing ability of a computer. An example of a floating-point operation is the calculation of mathematical equations. As such, FLOPS is a useful measure of supercomputer performance. MIPS is used to measure the integer performance of a computer. Examples of integer operation include data movement or value testing. MIPS as a performance benchmark is adequate for the computer when it is used in database query, word processing, spreadsheets, or to run multiple virtual operating systems. Frank H. McMahon, of the Lawrence Livermore National Laboratory, invented the terms flops and mflops so that he could compare the so-called supercomputers of the day by the number of floating-point calculations they performed per second. This was much better than using the prevalent MIPS to compare computers, as this statistic usually had little bearing on the arithmetic capability of the machine. Fixed point. These designations refer to the format used to store and manipulate numeric representations of data without using a decimal point. Fixed point are designed to represent and manipulate integers, positive and negative whole numbers. For example, 16 bits, yielding up to 65,536 possible bit patterns that typically represent the whole numbers from a 32,768 to plus 32,767. Floating point. This is needed for very large or very small real numbers, or numbers requiring the use of a decimal point. The encoding scheme used by the processor for floating point numbers is more complicated than for fixed point. Floating point representation is similar to scientific notation, except everything is carried out in base 2, rather than base 10. The encoding scheme stores the sign, the exponent and the mantissa. While several similar formats are in use, the most common is ANSI-IEEE-STD 754-1985. This standard defines the format for 32-bit numbers called single precision, as well as 64-bit numbers called double precision and longer numbers called extended precision. Floating point representations can support a much wider range of values than fixed point, with the ability to represent very small numbers and very large numbers. Dynamic range and precision. The exponentiation inherent in floating point computation assures a much larger dynamic range, the largest and smallest numbers that can be represented, which is especially important when processing data sets which are extremely large or where the range may be unpredictable. As such, floating point processors are ideally suited for computationally intensive applications. See also: Gordon-Bell Prize, orders of magnitude. References. External links: Current Einstein Atom Benchmark, BOINC Projects Global Benchmark, Current GIMPS Throughput, top500.org, linuxhpc.org, Linux High Performance Computing and Clustering Portal, winhpc.org, Windows High Performance Computing and Clustering Portal, OSCA Linux Cluster Ranking List by CPUs types and respective flops, information on how to calculate composite theoretical performance, information on the Oak Ridge National Laboratory Cray XT system. Infoscale Cluster Portal, Free GPL HPC, source code, pre-compiled versions and results for PCs, Linpack, Livermore loops, Whetstone flops, PC CPU performance comparison % flops megahertz, CPU, caches and RAM, Xeon export compliance metrics, including GFLOPS, IBM brings NVIDIA Tesla GPUs on board.